impossible right now. Well, it was wait, are you sure? Is it something on the lecture notes or?
定义的小问题，就是
作业，
像这个它
作业的话，我觉得是
就是 x t 如果是0的话，那我要就是它到底算不算可以相乘？可是它0我 y 也出不来。
为什么会有0？
就是如果今天在某个 t 的时候 x 会是0的话。
好，我们开始下课的问好，我觉得作业题目，对，我觉得下课对，就是有没有 lecture 的问题这样。OK， 抱歉。Okay, sorry. Yeah. So if you have question about lecture next time, you can ask right now. And yeah, if you have homework question, then yeah, you can come during a break. Okay. And yeah, so are people happy with the lecture next time? So this time let's run through very quickly. So we have some example of discrete time convolution. Okay, so we have derived convolution. Okay, let's run back a little more. So we derive convolution, and convolution is this equation. We found out that LTI system can be expressed by convolution. So the output of an LTI system is the convolution of input with the unit impulse response, where unit impulse response is a response to a delta function, unit impulse function. And then we found out that so to calculate output of a LTI system, we need to do this calculation of convolution. And convolution, well, mathematically it has this form, summation k summation of a dummy variable k from minus infinity to plus infinity, x of k and h of n minus k. Okay, and so this is convolution, and I can just throw this formula and let you do all the calculation, but we run through some example of convolution next time. So for example, we have convolution of this x of n and this h of n, and we found out that we have different way to visualize the convolution. First is we can think about x as different impulses, and then you have corresponding response. So this 0, 1 h of n and time delayed h of n, and then adding together will be your response. Then the other way is you try to draw x of k and h of n minus k as a function of k. So you can have x of k like this, and then your h of n like this, and h of n minus k will be the 0 will be dragged. The 0 point will be dragged to the n point, and then your function will be flipped left and right. So this 0, 1, 2 function it become h of n minus k. Then on the k line, you will be the 0 point become the n point, and then you have this plus 1 plus 2 become minus 1 minus 2. Okay? And then you can think about the overlap between x of k and h of n minus k for different n. Then you can calculate the y of n for different n. So you usually what you see is you drag the n from minus infinity to plus infinity, and then see how x of k and h of n minus k overlap on this line of k. And yeah, so when they have overlap, you multiply the overlap part together and the summing them over, and you get y of n. Y of n. And there are more example. So this is an example of exponential decay x and unit step h. Then you also flip this h around and drag it left to right. Okay. So your x of k will look like this, and h of n minus k look like this. And you see that for your n being less than 0, you have no overlap, so this is 0. And when your n increase, your overlap is summing over this exponential decay function. So the total sum is this saturating function. Okay? And then you have another example, and then we have this complicated example where we have two boundary on x, and so x has two boundary, and h also has two boundary, and h is this exponential growing function. And we found out that this is a very annoying, well, I shouldn't say annoying, but it's a very complicated calculation because you need to set up many cases of how they overlap. So you have n less than 0, they don't overlap. then n between 0 and 4, they overlap partially. Then n between 4 and 6, when you drag this function more and more right, then this has 4 overlap. And then n between 6 and 7, you have partial overlap again. And n bigger than 10, you have no overlap again. And in total, your function will look like this. So less than 0 have no overlap, and between 4 and 6 you have more overlap, and the overlap decay like this. Okay. I guess 0 to 4 and 4 to 6 are kind of different too. But anyway, this is a function. And finally, we have another function that's exponential growing from negative infinity. And once again, h of n is this unit step function, and we just draw h of n minus k here. And so you see this from negative infinity, you always have overlap between x and h, but the overlap is exponential growing. But once your n is greater than 0, then the overlap is staying the same. So the total function looks like this. So you have exponential growing when n less than 0, and once n is bigger than 0, the overlap stays the same, and you just have the constant output. Okay. Does everyone understand? The quick review of some example of discrete time convolution. Okay. If not, okay. Let me make sure. Okay. If not, then let's go to continuous time convolution. So we could go over this really quickly, but so it will be more detailed today. This is really very similar to the discrete time case. So we have a continuous time function, and we want to see what happens when we put this through a LTI system. And what we do is we mimic what we do in discrete time. So first we try to discretize this function into a lot of strips, kind of like a discrete time function. Okay, so we get back our those strip functions. So this is how we this is a function that we use to do like a finite version of delta function. Okay, so those rectangular functions, this is defined as so we have this delta subtriangle function that has height 1 over delta between height 1 over triangle between when time is between 0 and the triangle and the 0 hour where. So this function is just a strip between 0 and the triangle. And we can think about our continuous time function approximated by like a staircase. So this is what we do kind of in in calculus. So we think our function kind of look like a staircase that's partitioned by those small triangles. Okay, so for each triangle, then we think it's kind of constant between them, and you walk up a stair and kind of constant between them. And so we think our function is actually a sum of whole bunch of those delta triangle function with a different time advance or time delay. So we think this function is a summation of a whole bunch of strip function, and each strip is like this. So between this -2 triangle to minus triangle, then this thing has height x of -2 triangle. So the x is x of t is the original continuous time function we try to approximate with those strips. So this strip has a height x of -2 triangle, and and it's multiplying the delta subtriangle function and time shifted to -2 triangle. So delta triangle function was originally like here, and it's time shifted to -2 triangle. And the next one, you have the height x minus triangle, and the strip is time shifted to minus triangle. And and we have another function here, another one, x of 0. Excuse me. Okay. Anyway, what's going on? Sorry. yeah, and I guess I should start with this really. So this is a delta triangle function with height. Oh, so the height is actually x of 0 and times triangle. Because remember, okay, so this is really easy. Because the delta subtriangle function has height 1 over triangle, but the height is actually x of 0, so you need to multiply the triangle to cancel out the 1 over triangle. Okay, so let's just write this. So this is really easy. So x over 0 times the height was of this was 1 over triangle. Then you times the small triangle, then it's equal to x over 0. Okay. So the height of this thing is x over 0. That's why you have a delta of triangle and times triangle here. Okay. And yeah, so you time shift this delta sub triangle around, and then multiplying the x value later, and multiply a small triangle here to cancel your 1 over triangle. And you're adding all those together, you think you should have a staircase approximation of your continuous time function. Okay. And so everyone understand? Okay, everyone okay with this? And yeah, so you sum over all those things. So you sum over all those time shifts. Sorry, you sum over all those time shift k. Then your x is the summation k from minus infinity to plus infinity. X of k triangle, then delta sub triangle, and time shift to minus k triangle. And then you have this triangle here, just like you have the triangle here. Okay. And yeah, so this is your x of t. The finite version is just this part, and obviously we think if we take a triangle go to 0, and your function is smooth, then this will become your x of t. Okay. And indeed, we see this makes sense because if you take the delta equal to 0 limit, then this will become x of t equal to minus infinity to infinity x of tau delta of t minus tau d tau, and this is a shifting property. We are jumping ahead a little bit here, but we'll see this later. Okay. And yeah, so we have this discretized version of our x of t, and then with this discretized version, then we run similar argument as our discrete time version of LTI system. So first we say the system is linear, and we have a linear combination here. Okay. So we have a linear combination here, then our system is linear, so we'll get a corresponding linear combination. So we get the same summation k, and say coefficient x of k delta, and each of those delta of a triangle, those time shifted is this okay? Yeah, so each of those time shifted delta of subtriangle. Oh, sorry, I got left and right wrong here. Okay, so this thing I should, control. Yeah, so this left and right I got it wrong. So this you should swap those two. Okay, so this delta subtriangle. At t minus k delta, sorry, delta subtriangle at t minus k subtriangle. We just say if you put it through a system, it becomes some response function, k sub k triangle, h sub k triangle of t. Okay, so this thing goes through a system, becomes this h of sub k triangle of t, and this small triangle can be think of as part of the coefficient with this x of k triangle. Okay, so this is a linear combination, so this goes down, and the only function part is this time shifted delta subtriangle, and it got some corresponding response function. Okay, so I think yeah, so we think the response so we can write the response to x of t always as this y of t. That is expressed by those h sub k triangle functions. And okay, so we have this summation becomes this summation, and then now we go back to continuous time. So we set tau equal to k triangle, and taking a limit of triangle go to 0. So tau equal to k triangle makes sense because you see k triangle is kind of where you are at this at this time at this timeline. So K triangle is kind of like a T, and we just give another dumb variable named T as tau. Okay. So we say K triangle as tau, and we take a limit of triangle goes to 0. So we actually take the limit. Then we take a triangle goes to 0. Then the summation of K will become integral. So K from minus to infinity, then tau also become minus infinity to infinity. Okay. And x of K triangle, as we say, become x of tau. Then okay, so the T minus K triangle become T minus tau, and this delta subtriangle become delta function. This is because that's our definition of delta function. The definition of delta function is the delta subtriangle when triangle goes to 0. And then finally, this triangle here becomes just d tau. So it becomes an infinitesimal element on this dumb variable tau. Okay, so that's how we get. That's how we take this expression with limit triangle goes to 0 and get this nice integral. The x of t equal to minus integration minus infinity to plus infinity, x of tau delta of t minus tau d tau. And as we said, this makes sense because this is the shifting property you have seen. Okay, everyone understand so far? Okay, and yeah, and then we see the other part. Other part we have this y of t with a similar expression, and we take those limits. Then we see everything is basically similar except we have h sub k triangle here, and that just become h sub tau here. So h sub tau of t is some function depend on tau, and with dumb variable t. No, with the variable t same as this t. Okay, and so far we are following the discrete time derivation, and finally we said this is time invariant, and so using the fact that the system is time invariant, we can express the h sub tau of t as basically as h sub 0. Okay, because h sub tau of t is the okay, so maybe I should write one more equation here, because h sub tau of t is the correspond to this thing, right? So it's delta triangle of t minus k. I guess you can see here. So from those corresponds, you can see that delta of t minus tau is mapped to h sub tau of t, and you know if the system is time invariant, then delta of t minus tau is a time shift version of delta of t, and so this h sub tau of t should be a time shift version of h of t, which is also h sub 0. Okay. So by the time invariance, h sub tau of t equal to the time shift of h sub 0 of t, and just like in this one case, we call this h sub 0 of t as h sub t, and yeah, so swap everything back, then finally we get our convolution expression of output of LTI system. So y of t is the integration minus infinity to plus infinity, the x of tau just x of tau, and the h sub tau of t becomes h of t minus tau and d tau. Okay, and yeah, so this is the continuous time convolution, and we follow a derivation similar to discrete time. I guess the derivation is nice to know, but the most important thing is you need to remember the integration, and yeah, you need to do a lot of this integration to calculate the whole bunch of convolution. I guess a whole bunch of output of systems. Okay, and so notation is just like in discrete time. We write this integral. We think it is a convolution between two functions x of t and h of t, and this is defined as this. It's an integration from minus infinity to plus infinity, x over tau h over t minus tau d tau. Okay, does everyone understand? That's it. And yeah, and just like in discrete time, h over t is called a unit impulse response or just impulse response. And once again, h of t is the response of a system when the input is delta of t. Okay, so now this h of t is, I guess the h of t is a bit weird now, because the input impulse is this delta function, delta of t. And well, it's a bit weird because it's not really a function, it's a distribution. Remember, the delta function is this delta subtriangle when triangle go to 0, so it has infinite height at 0 and 0 otherwhere. Okay, so delta function. Draw it here once again. Delta function is this weird function with spike at 0. Okay, and so height is 1, but it's really infinite. So we say 1 here, but the height is really infinite, and we think this function has area 1. Okay. So this function is value is expressed by, if we integrate through it, it has area 1. Okay, that's a delta function. So that's right, that's delta of t. Okay, so that's a continuous time integral, and just like discrete time integral, that's a continuous time convolution, and just like the discrete time convolution, we'll have a lot of example and some homework and test what's the convolution between some x and h. Okay, so let's see some of them. So this is similar to what we see. So we have x of tau, that's exponential decay starting from some time, and h of tau is a constant. Okay, and really the result is similar to the discrete case. So you also do the time shift. So you also want to plot this h of t minus tau as a function of tau. Then you do this integral. Okay, and so you have h of t minus tau. So first part, h of t minus tau as a function of tau. So similar to discrete case, your 0 become t. Okay, and you flip left and right around. So 0 goes to t, and the left and right got flipped. So your function looks like this. And you drag the t from minus infinity to plus infinity, and see how they overlap with your x of tau. And yeah, so for t less than 0, this thing and this thing has no overlap. So your output is just 0. And for t bigger than 0, then your overlap is between 0 and t, right? So because less than 0, x of tau is 0, then bigger than t, then h of t minus tau is 0. So your overlap is between this 0 and the tau. So here the important thing is this. So tau is between 0 and t. Okay, so you only have overlap between 0 and t on here. I'm saying this is the overlapping area. Okay, so here, and yeah, so your y of t is this integration x of tau h of t minus tau, and it's basically this integration of x of tau from 0 to t. And you can do an integral, and it's this function. Okay. 1 over a, 1 minus e to the minus at. This is basically the integration with exponential function. Okay. And then you can combine everything together and plot your y. So y for t less than 0 is 0, and for t bigger than 0 is this exponential saturating function. When t goes to infinity, go to 1 over a. Okay. So this is kind of similar to one of the example we see in discrete time. Let's see if we can jump back. Yeah. So it's similar to this function, right? So this function is also x of t exponential decay and h of n. So x of n exponential decay, h of n constant, and then we see it's saturating to somewhere. And yeah, so now it's similar. And this is a similar continuous case. This is saturating function. And if you want to write those two cases together, yeah. So those are cases of y of t. Okay. For t bigger than 0 and t less than 0, if you want to write both of them together, then you can use u of t like this. So you cut off this function at t equals 0 by having a u of t here. Okay. Does everyone understand the continuous time convolution? Okay, seems okay. Okay, that's okay. Then we're actually a little faster. Okay, let's see how much we can teach. Okay, then let's go. Question? No. Yeah, let's go to the next part. So we now know the systems, LTI systems are described by convolution with the unit impulse functions. Then there are some properties we want to talk about. So first is we want to talk about properties of convolution itself. Turns out convolution is a property that is commutative and distributive and associative. So basically it just behaves like the multiplication of scalars. So that's really nice. And then second part is we want to describe the systems by the system function. And so we found out LTI system can be described by the system function. I guess we haven't called it system function yet, but we can find out it can be described by the impulse response function h. And that also means that this four property that we talk about a lot on chapter 1 can also be described by this unit impulse response h. So it's memory and the invertibility and the causality and stability. You can all determine them by looking at your impulse response h. Okay. And there are other things that's a bit less important. Okay. And yeah, so before we go to that, let's say something else first. Okay. So we have said that LTI systems, so linear and time invariant systems, are completely determined by the unit impulse response is h function. Okay, so we say for describe LTI system, the output is discrete convolution between your input function and your unit impulse function h, and the convolution is this summation x of k h of n minus k. And for continuous time system, it's similar. So your output is totally dependent by this h of t, because it can be, if you have some input x of t, you can just calculate the convolution. That's the integration of x of tau h of t minus tau d tau. Okay, and but once you want to stress is that this completely determined thing only works for LTI system. So if you have some systems that are not LTI, then they can have same impulse response h, but they are different function. So for example, we think about some impulse response, a very easy impulse response. Okay, so the impulse response is basically two delta functions. So impulse response of being 0 everywhere and 1 at n equal to 0, 1. Okay, and with this impulse, okay, so this is basically let me write. Okay, so h of n is so it has two spikes at 0 and 1. So h of n is basically delta of n plus delta of n minus 1. Okay, and then your y of n, you can calculate its convolution. So your y of n you can calculate convolution with h of n, and you will find out that it will be x of n plus x of n minus 1. So this delta of n will give you x of n, and this delta of n minus 1 will give you x of n minus 1. Okay. And but so yeah, so if you have a LTI system and they have this impulse response, then you know that the input output must be related this way. But we can have two different systems different from this xy. So this is our description of the LTI system with this h. But we have two different systems that also have the same impulse response h. Okay, and yeah, and they are not the same as this system, and that's because they are not LTI, so they can be different. Okay, that's why they kind of seem to contradict this statement. That's because this statement you really need LTI system. So we just have an example here. So y of n equal to x of n plus x of n minus 1 squared. So this is different from this system. And but you can check the impulse response. So you can put x of n equal to delta of n inside. and x of n equal delta of n inside, then y of n will be delta of n plus delta of n minus 1 and squared. So that's basically h of n squared. Okay. But you see 1 squared is 1 and 0 squared is 0. So when you put h of n as sorry, when you put delta of n as x of n here, then you see the output is still this h of n. And similarly, you have y of n as max of x of n and x of n minus 1. And so if x is okay, so if x of n, so here what we want to do is x of n equal to delta of n, x of n equal to delta of n, and yeah. So you see that if you take the max of so x of n is 1 spike is n equals 0, okay, n equals 0, and y of n equal to max of x of n and x of n minus 1, and so at each point you look at the value of x and x n minus 1 and see what's the maximum, and it's all 0 except at n equal to 0, then this maximum is x of n equal to 1, and that's 1, and at n equal to 1, okay, so think about it, n equal to 1, then y of n is maximum of x of 1 equal to 0, but x n minus 1 equal to 1, so y of 1 also equal to 1. Okay. So anyway, you see that when x of n equal to delta of n, then y of n for this function also equal to this h of n here, and yeah. So they have the same impulse response, but there are different systems in this system. Okay. So that means that when you take x of n equal to delta of n, it's already written there, so I shouldn't write it again. Okay. Yeah. So so that means when you take x of n equal to delta of n, a lot of different systems will give you the same response h of n, but yeah, if they are not LTI. But if they are LTI, then this x of n equal to delta of n response will determine the whole system. Okay, so that's something to stress on. Everyone understand? Okay. And yeah, then let's finally go to the properties of convolution. I think it's more interesting, the property themselves is more interesting than the proofs. So the first property is commutative. As I say, is the property makes the convolution like a multiplication. So first is it's commutative. So x convoluted with h equal to h convoluted with x. Okay, and it's similar, is the same for the continuous time. And the proof is really simple. So I will just say how you do it. So the proof is you do change a variable. So you just write down those two things. So I guess you write down this. So this is by the definition of convolution. Summation x of k and h of n minus k. Then you just changes k to some n minus k prime. And yeah, so you do a change of variable from k to some k prime, and you will arrive the other side. And similarly, for continuous time, you also do a change of variable. So you change the dummy variable tau to some tau prime equal to t minus tau prime, t minus tau, and yeah, you will get this. Okay. And yeah, so first is commutative, and second is distributive, and second property is convolution is distributive. So that means x convoluted with the summation of some h1 and h2 equal to x convoluted with h1 and x convoluted with h2. And similarly, you have the same thing for the continuous time case. And then from this, you can start do something interesting. So we see that when we have this serial connection of parallel interconnection of two LTI systems described by H1 and H2, then this is actually same as you have your x of t go to one LTI system with the impulse response being H1 plus H2 here. Okay? So you find out that we can do this kind of simplification of our interconnected system. And the proof, the proof you can once again you can write down the definition of convolution and see this really easy. And we also have a more fancy proof here, so I guess it's less fundamental. You can also have a fancy proof by using the commutative property that we just claim being true. Okay, so first we know that our system is linear. So if our input is x1 plus x2, then the output should be x1. So the input is x1 plus x2, then the output of x1 plus x2 is convoluted h should be the output of x1 and the output of x2. Then the output of x1 is x1 convoluted with h, and the output of x2 is x2 convoluted h. So first we can get the distributed law on the left hand side. On this reverse order just by the linearity of the system. And then you use a commutative property, then you can swap this h and x1 plus x2 and h with x1 and h with x2 here. And then you just change your variable name, so you change your x1 x2 to h1 h2 and change x to h. Then you arrive this equation, and that's the distributive property we want. Okay. Yeah. Everyone okay? And yeah, so distributive property and the commutative property makes calculation of a convolution much easier. So now we can have a more complicated function of x and do convolution with h. So we see that, so for example, our x of n equal to this exponential decaying part plus the exponential ingrowing part. So we have 1 over 2 to the n u of n plus 2 to the n u of minus n. Okay, we have these two parts. And then we want to convolute it with our h of n equal to u of n. Then we found out that x is the summation of two parts, so the output is also the summation of two parts. So it's the first part convoluted with h, and the second part convoluted with h. I guess in this example we can just see this by linearity, but anyway. Yeah, so the output is y1 plus y2, y1 being the first part convoluted with h, and y2 being the second part convoluted with h. And so what is y1 and y2? We're kind of already seen that, right? So y1 is this exponential decay with cutoff at t equals 0, with n equals 0. So y1 is like this example 2.3, and so we know y1 look like this. This is a saturating function, and y2 is this exponential growing function. Let's see, it's the same thing, right? Yeah, y2 is this exponential growing function, and they convoluted with h, and we know y2 look like this. So so the total function look like this. So it's y1 is the saturating, so if y2 is growing and saturating at 2, and plus the y1 is the saturating function. Let's see. So the t equals 0 is a little weirder. T equals 0, it should be 2, and this should be, I think this should be 1 when alpha equal to 1 over 2. Or is it? Yeah, I think it's 1. Anyway, yeah, so this is the result of the y1 plus y2. It's exponential growing, then exponential in saturating, and they have a big jump at t n equals 0. Okay. Any question about the distributive property? If not, then let's go to the next property. So multiplication, the next one is associative, and this is really nice. So it says that if you want to convolute x, so you have three things convoluted together, x convoluted with h1 and convoluted h2. Then you can convolute h1 with h2 first, and that will be same as you convolute x and h1 first. And yeah, similarly for continuous time. Okay, so this is associative. So you can write this convolution, you can deal with the chain of convolution in whatever order. So you can do the later part first, or you can do the previous part first. And the proof, I think proof is also you write down the equation and then you can see it. But anyway, proof, you want to see a proof is in one of the problem. Okay, but it's it's still some basic arithmetic, integration or summation, and then maybe some change of variable or a change of summation order. And but this is the more interesting thing is the property itself. So first, as we said, this property make the convolution like a multiplication, and so that means that you can just write the chain of convolution without ambiguity. Okay? You can just say y of n equal to x of n convoluted with h1, then convoluted with h2. It just means you can associate them with whatever order, and this is the chain of convolution. And also y of t, so also the continuous time version, you can have y of t equal to x of t convoluted h1 and convoluted h2. Okay. And so those three properties is really, really important to remember that, because they can make a lot of calculation associated with convolution a lot easier. And we will derive properties with them. Okay. So once again, so this, let's finish the associative property. So one thing you can do is you think about this serial interconnection of system. So you have x of t going through some h1 become w of n. Sorry, x of n going through some h1 become w of n, and going through some h2 become y of n. And so you know y of n will be x convoluted with h1, then convoluted with h2. But now you can combine this h1 and h2 into some h. That's just a convolution of h1 and h2. So you know that if h1 LTI system, h2 LTI system, then the serial connection of two systems is a system with this impulse response h1 convoluted with h2. Okay. And so this is really something new we learned from this associative property, because before we just think this h is impulse response to some input, but somehow, and convolution is just how you get some input to some output. But now we are convoluting something into impulse response, and somehow that's still something meaningful. If you convoluted the impulse response of two systems, you found out that that's the impulse response of those two systems zero together. Okay, and even more interesting. So h of n equal to h1 convoluted with h2. Then by our associated commutative property, we know that h equal to h2 convoluted with h1. Okay, and then we can break it up again and see this as you do h2. You put the h2 system here, then you put the h1 system here. So what we're showing is that we prove that you can change the order of two LTI systems. So you go through h1 first and go through h2 system first. That's h1 system first, then h2 system second. The same as you go through the h2 system first, then h1 system second. Okay. So you see those three properties can really give you a lot of insight on how you put the LTI systems together. And the LTI system, once again, they are completely determined by those impulse response and function h. Okay, that's interesting application of the properties. So everyone understand? Okay, any question? No. Okay, we have 5 more minutes, I think. Okay, I guess we can have a quick review of the properties again. So once again, we have 3 properties. So commutative, that means that you can change your order of convolution. So x convoluted to h, same as h convoluted with x. And distributive, that means when you convolute it with some linear combination, the same as you convolute it and do linear combination. So x convoluted with h1 plus h2, equal to x convoluted with h1 and x convoluted with h2. Okay, and then finally associative. So x convoluted with this parentheses h1 convoluted with h2 equal to x convoluted with h1 then convoluted h2. So really you can write the chain of convolution and it's unambiguous. Okay. So that's the three property of convolution, and we see that it's really like a multiplication, and that's why we write it kind of like a multiplication. We just write a star here. Okay, and then I guess for 5 minutes, let's go to the first property first. So first property of LTI system of describing LTI system through this impulse response H is where the system is memory. Okay, and and let's remember what memory or memoryless is. So memoryless is defined as a memoryless system is a system where the output at any time only depend on the input at the same time. Okay, and yeah, so output at any time only depend on input at the same time, and you can derive that the system is memoryless if and only if the system function is 0 when n equals 0. That means so for discrete time, for discrete case, the system function is 0 when n equals 0. That means the system function is just one spike at n equals to 0, and let's call it height k. So the the impulse response is just some constant k times this unit impulse delta of n. And we can derive this result like this. So we think about what should be y of 0. Okay. So y of 0, it should only depend on x of 0. But you write down the convolution, then y of 0 should be summation k from minus infinity plus infinity, h of minus k, x of k. So this is just writing on the convolution with n equals 0. Okay, and we can plot our x of k and h of minus k. Okay. So x of k is some function here, and now we think about you have some h of minus k here, but you want this summation to only depend on x of k. Okay. So x of k has a different value everywhere, but you want this summation depend only on x of 0 here, right? So you have x of 0 here, something. X of 0. And yeah, but you are multiplying everything together and adding it together. So if you want this summation to only depend on x of 0, that means this h of minus k can only have a spike at k equals to 0. Right? So this is at k equals to 0. And yeah, so h of minus k only have a spike at k equals 0, then h of k or h of k also only have a spike at k equals 0. And that means x of n only have a spike at k equals 0. And okay, so this is slightly confusing, so this k has nothing to do with this k. Okay, so those are two different k. This dumb variable k is k being summed over, and we have another k that just height here. Okay, and so maybe that's okay, that's annoying. Let me mark it here. So this is on k bar here. It's a different constant. K bar. Okay, yeah, so that's a derivation or argument of why h of n need to equal to some k bar and delta of n. And then when you try to convolute this with some x of n, then you see that x of n convoluted with delta of n just get back to x of n. And by the linearity of a convolution, the y of n equal to k bar x of n. And then similarly for continuous time, you find out the h of t needs to be 0. Needs to be 0 when t not equals 0. So your h of t is some constant times your delta function. Okay. And yeah, so we are exiting on time. And so let's take a 10-minute break. and then we'll continue with other property in next class. Okay.
我刚想问是，就是这个，因为它在分母，然后它长那个样，对，它在分母，所以
对啊，这
我们要考
个题目是什么？
就我只想问说，我们要不要考虑 x7有为零的状况？
等一下我看一下，这个题目是在问说，
要证它的相加性跟相乘性。
相加性跟相乘性。x 有7是0的时候，它就 undefined。我觉得应该，我想想看，所以我们有些 input 是 undefined 的，我觉得应该不用考虑了。对啊，就不用考虑了。因为那样，
就不用考虑。
对 undefined 就不要考虑。
所以我们只要考虑要 define 就好。
对。应该，等一下我想想看，所以你是说的呀？我想想看，所以相加，所以可能，
因为相加已经不是就是所以它。
所以你说它加的，它可能会跑出定义的区间呢？
相加已经就是它没有相加性，所以。
已经没有了。
对。
它已经没有，那就也还。
是那个 homogeneous 的话。
你说乘以0之类的事情吗？
就是只要 x t 是0，这个就没有东西了。
那我想一下，太奇怪啊，乘以0，然后再有 define， 那就。想想不乘0的话有，乘0的话会很奇怪。我觉得那就不考虑乘0的好了，因为它还蛮，而且就乘0的比较奇怪啊，乘0的先不管好。这只是说这两个方选你放 x o t、x o n 是由它分进去的话，那 y 都会等于这个方选这样。对吧？你要去算一下，但是其实也不是很重要。但就只要跟你讲，不是有 TIC 乘的话，就是它可以有一样的 impulse response。impulse response 是说 x 放 h 给它，然后跑出来 y 是什么东西，然后他会说这两个方选，这两个 C 乘，它其实跟这个 C 乘是不一样的，就这三个 C 乘都不一样。然后说这两个 C 乘的这三个 C 乘的 impulse response 都是这个 h。那这跟我们之前说的不太一样，因为我们之前说是，也没有说不一样，但我们之前说的是，如果你是有 TIC 乘的话，那 这个 H 就应该完全决定你的 C 乘是什么。但是那这三个 C 乘还是不一样的原因，是因为他们两个没有 TI， 就这样。所以，这是在讲，其实在讲很细微事情，对，所以首先我们要讲这句话，你要很注意，就是我们之前应该说这里吧，对，我们不是说有 TIC 乘的话，我们知道 H， 那我们就可以从 x 变出 y 嘛，因为我们可以直接算这个东西。所以如果你是有 TIC 乘的话，你知道 H， 你就完全知道你的 C 乘会怎么做，你就每个 x 可以变出每个 y。对，那我们说，那我们有个 C 乘，它的 H 是这个东西。对。
老师，我的问题就是在什么情况下我会提前知道 H of t？ 就是你不是说知道 H， 你就可以知道。
这可能题目会给你之类的啊。
那在现实情况中，应该是先得到转换的结果，而不是先得到。
因为现实情况你会设计某个 HOT 出来，你会设计你的系统，就你会想你系统要做什么事情，然后去设计那 HOT 嘛。对啊，之类的。对。对，那这里是在说你这里其实是很思维细节的事情，是在说你这句话你要注意说这个只有对 LTIC 乘是对的，就是只有 LTIC 乘你才可以直接靠 convolution 去算出从你要 input 算出 output。比如说这两个不是有 LTIC 乘，那他们也有某个 impulse response H， 但是他们跟这个 C 乘不一样。就是这个 H 它决定有 TIC 乘是这个，
对，这个 H 是一个 C 乘。
对，H 是就你只看 H 的话，它是一个方选，它就是某个方选嘛，对，它是某个方选，然后方选，所以这也重点说方选再加上 LTI，然后你可以算出这个，就是照这个 H，然后如果它是 LTI 的话，你算出来的 X 跟 Y 的关系是这样子，就是去算这个 convolution 它会这样子。
是 H 是 LTI 的时候，
不是
C 是 LTI 的时候。
有一个 C 胜是 LTI 的时候，对 ，H 是方选 ，H 可能是 H 是 impulse response，
所以要先把这个写出算式来，再去看它是不是 LTI 的。
不是 LTI 你才可以用这个算式。
啊？那怎么知道这个是不是 LTI？
就会告诉你是不是 LTI 这样子。对，你要假设你是不是 LTI，或是，但是有不同的说法，就是例如像这两个东西就不是 LTI，就是 C 层你有不同的说法嘛，你有不同方法表示法。你可以说，例如说我的 C 层是 LTI，对吧？我可以，抱歉，我擦掉，对吧？就 C 层有很多不同表示法嘛，那我们现在讲了一堆有 T I C 层，那例如说我的 C 层是有 T I，然后我再给你的 H of T 好了，那我就知道我的 C 层是什么东西了，对吧？那或是像这里的话，我就会发现说，我可能不是有 T I，那我给了下面这里想要说的是我那的有 T I 的话。那我给你的H of T，其实我还是不知道我的 C 层是什么东西，因为我可能还是有很多不同的 C 层的。对。然后要记得 H of T 的定义是，H of T 的定义是 delta of T 会变数 H of T 这样。然后那如果不是有 T I C 层的话，那我们可能就要给一个从 X of T 变出 Y of T 的方法这样子。我们第一章有很多定义 C 层方法，例如说我可以写 differential equation 之类的。所以就是让你回想起来，说第一章我们说我们有很多不同的 C 层，然后他们是 X of T 会变成 Y of T 的。那只有在有 TI C 层的时候，你可以直接给 H of T，然后就是用 convolution 算。那如果它不是有 TI 的话，那你不能直接用 convolution 算出它的 input output relation。
所以就是如果是 LTI 的话，这个 C 层可以用 HT 算出来。
对。然后如果不是的话就不行。
他没有办法，这个已经他没有办法把它拆成。
他没办法拆成 convolution，他不是 convolution。
他没有办法拆成 convolution。
没有，他不能拆 convolution，但你还是可以算 impulse response 的。你还可以说，那 impulse response 就只是定义成这样子嘛。你还是可以算说我丢大方程进去，然后它会跑什么东西出来嘛。就是这样的，所以说这两个东西你可以丢它的方程进去，然后跑出来的东西就会长这个样子。但是因为它没有这 convolution 的事情，所以你不知道丢其他东西进去，它会跑什么东西出来。
那这样子在不是就是 linear time invariant 的系统底下，那个 H of T 就没有意义了。
对啊，但就只有个 impulse response 的意义，但不是很有用，因为你不能算其他东西。对啊。
所以就是这两个 system 它是可以丢那个。
你可以丢这个 x 等于丢它进去嘛，然后会跑出某个东西，然后发现这个东西跟这个一样。
丢那个跑出 h， 然后会跑出这个，可是它没有办法。
对啊，例如说你丢个 time shift 的丢它进去，你会发现跑出来的东西就不是 time shift 的 h 出来了，对啊。
所以如果只有 h， 我们也不知道 c 是在什么。
time shift 其实都没会 ，anyway， 但他们不是有题，有些怪怪的部分，这个好像有翻译别人，刚看一下，不确定 ，anyway， 然后
这两个没有理解。
他们好像没有我们理解题，我刚才在重申，好像陈述字会不一样，对。
所以如果只有给 H of T， 然后我们无法倒推出它的 C 层是什么。
对啊，只给 H of T， 然后没有告诉你说这有 TI 的话，其实你不知道 C 层是怎样。
老师，我想问一下，就是这个观念的部分，我想问一下，就是我还是就这感觉不是很直觉，为什么一个 LTI 系统会直接表示成这样？
这不是我们证了很久吗？
你说刚刚那个就是证明吗？
不是啊，就前面这个时代，前面的那几个时代就是在证这件事情。
这些吗？
对啊，这些东西啊。我不是在说，如果是 linear 的话，丢它会变出这个 h 等于 k， 然后如果是参与别人的话，那 h 等于 k 会变成这个 h over minus k。所以我就推到这个东西啊，这个不就是 convolution 吗？对啊。
Okay. Okay. Yeah. Okay. Any question yet? I guess people seem very confused about this, so let's say this once again. Okay, so this first slide. Yeah, the only thing I want to say is we have been describing system by this impulse response h of t or h of n, and really the only thing I want to say here is if you want to describe a system by its impulse response h, then the system needs to be LTI, because you have these two different systems that's not LTI, and you know their h, but you still don't know how they respond to other things. Okay? So yeah. So if you want to use a convolution to calculate your system response, if you want to use this h and the convolution to calculate your system response, then you need to make sure that you know your system is LTI. Maybe the problem will tell you, or maybe you will design your system as LTI or something. But yeah, it's important to have your system being LTI here, so you can apply the convolution to calculate your input and to calculate your output from your input. Otherwise, so here in these two examples, you know how the system responds to this delta function, and let's say as is h here, but you don't know how the system responds to all other functions. Okay, because you cannot just use convolution to calculate the response of those two functions. Okay. And yeah, so you need to go back to do some dirty work to calculate. Okay, but yeah, so that's kind of a small point to remember. For a lot of the class, we were dealing with LTI system, but also some non-LTI system, but most of them are LTI system. Okay, so yeah, back to calculating, back to property of convolution and impulse response. So yeah, once again, convolution is like a multiplication. You have a commutative property, and a distributive property, and associative property. And I guess here we also use another property. So this calculation here, we also use a property that the convolution is kind of linear. So so here to derive this result, we have y of n equal to x of n convoluted with our k bar delta of n. And first we use that it's basically linear, so if you have multiplied by a scalar here, then it's k bar and x of n, and convoluted with delta of n. And we'll see this a lot, but basically the convolution with delta of n will be just this is basically identity. It will back to just x of n, k bar x of n. Okay. And yeah, you can check this easily by yourself. So function convoluted with delta function or unit impulse is back to the function itself, and is similar with the continuous case. So continuous case, if you have whatever function convoluted with delta function, then that's the C. So when you write this down, this is basically a C-fitting property, and you will get back to x of n or x of t. Okay. And yeah, so you see that LTI memory system is very simple. It's just the output is just a constant times the input. And yeah, similarly, output is constant times the input. Any question? Everyone understand? If not, sorry, yeah. So if everyone understand, let's go to the next property. Okay. So the property is that invertibility of LTI system. Okay. And remember, invertible means that you can find the inverse system. So you have on X, and go to system 1, become Y, then there is another system 2. Then there is the inverse system S minus 1, and such that output W will equal to X. And to derive the invertibility, so we first need to kind of another statement that's proven in homework in problem. So problem 2.350 will say that if the LTI system is invertible, then this inverse system is also LTI. Okay. So yeah, if we believe this, then we see that we can describe the invertibility of LTI system by saying that, well, you have this LTI inverse. The LTI inverse is also described by some impulse response H1. Okay. So we say if your system H is invertible, then there is another system H1. And then this H1 needs to satisfy that H convoluted with H1 equal to delta function. And that's because you think about your string, your system together. So you have an input X, then go to H, then go to H1. Then by our associativity, you have X convoluted with H, and this is H convoluted with H1 first. And then this will become the delta function. And as we just claimed before, X of n convoluted with delta of n will equal to X of n. Okay. And similarly for the continuation case, you have H of t convoluted H1 of t equal to delta of t. So that's invertible. Any question? Okay. Then yeah, let's see a bit more example. So we have H of t equal to delta of t minus t0. Okay. And when you convert it with X of t, then you find out that it's actually this function actually do a time shift on your X of t. This become X of t minus t0. Okay. So this is time shift. This is time shift, and this is actually an important property to remember. So this identity. So we are kind of smuggling important systems here. So one of the important systems we're seeing is those delta function. We see that if you have a delta function, then you convolute with a system. So the delta function basically corresponds to the identity system. So if you convolute it with delta function, then you get back to your original function. And then a large class of a system that's related to the delta function are those time shift functions. So it's a time shifted delta function, and you can check it easily by yourself that if you convolute your system with convolute your input with convoluted your input with this time shifted delta function, then you have a time shifted input as your output. So this is X of t minus t0. Okay. And anyway, so that's the time shift. And we back to what we talked about. We want the invertibility. So invertibility, then we want to find something that invert the time shift, and and very intuitively, then you just want to do a time shift as the inverse direction. So instead of time shift by t0, you do time shift by minus t0. Okay, and then you see that your output. So if you convolute your output y of t with this h1 function, then you get y of t plus t0, and that's just x of t. And you can also see that h1 convoluted h1 of t equal to delta of t, because that's h. So that's this delta of t minus t0, and getting some time delay. And so this t get HR plus t0 here, then this become delta of t. Okay, and yeah, so two time shift with negative directions, they will be inverse to each other. It makes sense. And you see that this h of t being time shift is invertible. Okay, questions? Now, then let's see more example of invertible systems. Okay. And this is a more complicated system. So h of n, actually we see this a lot. So h of n equal to u of n. We're seeing a lot of convolution with this u of n. And if we write this convolution out, then we find out that y of n equal to x of n equal to the summation. We actually use m instead of k for some reason. So summation n from negative infinity to infinity, x of n u of n minus n. And so u of n minus n is greater than 0 only when m is less than n. So this n here just goes to, so when you do this summation, then you find out that this n here just go to this n here. Okay, so you just summing over x from minus infinity to your time n. And this is actually our accumulator. So you accumulate all the pace signals up to now. Okay, so you find out that this h of n equal to u of n corresponding to accumulator. So you sum over all the pace signals. So maybe let's draw some schematic here. You have some x of n and let's say n here. So you have x of n like this, and there's some time step n, then y of n is the summation of all the pace up to now. Okay, so this is the accumulator. It's like a bank account with no interest. And anyway, so but back to the invertibility, and is this h of n being invertible? And the answer is yes. It's not so obvious, but we just write down the inverse h1 here. Okay. So inverse h1 is this delta of n minus delta of n minus 1. And we can use all the properties. We have learned to do the calculation here to show that the convolution back to delta function. Okay. So y1, so we want our y convoluted with h1 is back to x of n. And that's because y convoluted is h1. So you use the distributive property. So that's y convoluted with delta, that's just y, and y convoluted minus y convoluted with delta n minus 1. And as we said, delta of n minus 1 is a time shift, and that's just y of n minus 1. Okay. So this is y of n minus y of n minus 1. And because it's accumulation, so the difference between you sum up to n and sum up to n minus 1 is just whatever value you have x at n. So yeah, so your bank, so your summation to n and your summation to n minus 1, you take the difference, then that's what you put in today. So that's x of n. And you can also just do the convolution between h and h1, and you see the u of n convoluted with delta and delta n minus 1, and that's delta of n, because this is the first difference property of u of n. So I guess I should write the intermediate step here. So h of n convoluted, so u of n convoluted with this thing, then that's u of n minus u of n minus 1, and that's delta of n, as we shown in chapter 1. Okay, everyone okay with this? Okay, and then we go to next property. That's a bit more complicated, but anyway, this causality. So causality is similar to memoryless, but now we have more freedom in our h of n. Okay. And the result we get is this. So the system is causal if only if h of n equals 0 for n less than 0. Okay. And you can kind of derive this by thinking about y of 0 once again. So we think about, so if the season is causal, then y of 0 should not depend on x of, So if the season is causal, then the output at time 0 should not depend on input at time less than 0. Okay, and then we write out the convolution thing. So we have x of k. So y of 0 should be this multiplication sum between x of k and h of minus k. And you see y of 0 should not depend on this positive x, right? This x of k bigger than 0, it should not affect y of 0. And that means this h of minus k should only have amplitude, should only have things when k is less or equal to 0. Okay, and then you flip back this h of minus k to h of k, then you see h of k should only have response to k greater or equal to 0, and that means the h of n should only have response for n greater or equal to 0, and that means this k less than 0 part or n less than 0 part should be all 0. Okay, so that's a kind of the derivation. And yeah, so you think about y of 0, then you see that h of k greater than 0, h of minus k for k greater than 0 should be all 0, and that means the h of k for k less than 0 should be all 0. Okay. So these parts are all 0, these parts are all 0, and these parts are all 0. That's the important thing. Okay. So that's causal, and as we see, causal is less restricted than memoryless. Let's say you only have non-zero at this h equals 0, but causal says that half of them are 0. Okay, and another way to see this is to check the impulse response. Okay, and yeah, so this makes sense because you have a causal function. Then you remember this h of k is the impulse response. Okay, or h of n is the h of n is the impulse response. So you think you hit your system with the impulse at n equals 0, and the system is causal, so it should stay 0. It's causal in LTI. Okay, so it's kind of important that it's also LTI. But anyway, the system is causal in LTI, and so it should stay 0 when there is nothing, and it's causal. So only after you see hit here, then it responds with something. So that's another way to visualize why h of n is 0 when n less than 0. It's because the system is causal, so if there is no input, it should have stay no output, and finally hit it with some input at n equals 0, then it responds with something. Okay, so impulse response is 0 before the impulse occurs. So yeah, and anyway, the thing is system is causal if only if h of n equals 0 for n less than 0. And for continuous time is similar, so h of t equals 0 for t less than 0. Okay, everyone understand? Okay. And okay, the next slide we have a little implication of this, and I guess the implication we don't actually use it too much, but we write it here. So if you have this h of n equals 0 for n less than 0, then you can write two different convolutions. So you have the convolution x with h, then you have the summation x of k, h of n minus k. Then because h of n equals 0 for n less than 0, so the summation instead of minus infinity to infinity, you only sum to n, because for k bigger than n is this h of n should be 0. And otherwise you can have h convoluted with x, and you see the summation should start from k equals 0. And it's similar for continuous time. This x convoluted to h integration only up to t, and for this h convoluted to x, this integration starts from 0. Okay, this is just this property, and you see it in this convolution integral or convolution sum. Okay, then now we have some question that we can try to wake people up. Okay, so if h of n equal to u of n is a system causal. So if you think system is causal, raise your hand. Okay. And if the system is not causal, raise your hand. Okay. So I think yeah, people are good at this, and the answer is yes. the system is causal because, well, U of n for n less than 0 is all 0. Okay, now the next question is harder. It's a trick question, so be careful. If h of t equal to delta of t minus t0, is the system causal? If you think it's causal, raise your hand. If you think it's not causal, raise your hand. If you think the answer is maybe, then raise your hand. Yeah, this is a trick question because it depends on t0. Yeah, so for so it's a spike and so this thing is a spike at t equal at t0. Okay, t0. And as we say, so the system is causal if this spike is if you have nothing at t less than 0. Okay, so it really depends on where this t0 is. So for t0 greater or equal to 0 is causal. I guess I should just write yes. Okay, if t0 is greater or equal to 0, the answer is yes. And if t0 is less than 0, the answer is no. Okay, so this is a trick question. Okay, any questions so far? Okay, and I think that finally we get to the last one, stability. Okay, stability is complicated. It's complicated with our system function, with our impulse response, and still complicated on system. And it's more confusing with impulse response, so be careful here. Okay. So let's first recall what is stable, the definition of stable here. Okay. So the stable definition of stable of a system is that you need to look at the input and output. So if your input is bounded, if for every input, every bounded input you get bounded output, then your system, we call this system stable. So this is BIBO. You have bounded input and you have bounded output. And we also have a reminder of what bounded means. Bounded means that there is some finite number such that your signal is always, the absolute value of your signal is always less than some finite number. Okay? And only right for discrete time, but it's similar for continuous time. So anyway, and let's have the result here first. So how you describe whether your system is stable by the impulse response h is you calculate this thing on your h. You check whether your h is absolutely summable. Okay. And that means you sum over the absolute value of h from minus infinity to infinity and see whether that's a finite value. Okay. So if it's a finite value, then your h is absolutely summable, and yeah, then your system is stable. And for continuous time, it's similar. You want to check where your h is absolutely integrable. And absolutely integrable means you take the absolute value and the integration from minus infinity to plus infinity. If this is a finite value, then your system is stable. If it's not a finite value, then your system is not stable. Okay. And okay. Then let's do a partial proof of our claim. Okay. So we claim that for your LTI system, okay, so let's only do discrete case. So we claim that for discrete case, your system is stable if only if this equation is true. So means your h is absolutely summable, means absolute value of h summing from minus infinity to plus infinity is some finite value. Okay, and proof has two parts, so we only prove one part of it. So it's sufficient and necessary. So let's prove sufficient because it's kind of easier. So sufficient means that if this is if this is satisfied, then our system is stable. Means bounded input, bounded output. So let's assume we have this thing and we have bounded input, and let's calculate its output. Okay, so bounded inputs on x with x of n less than b for n, and what's the output? Well, we have our impulse response here. So we can calculate our output by just doing convolution. So let's just write down convolution. And well, convolution is commutative. So there are two ways to write it. We choose to write h first. So this is h convoluted with x. So summation k from minus infinity to plus infinity. Then h convoluted is x. So h of k times x over n minus k. We write it this way because we know this is the easier way to go. Okay. So yeah, so y we just write the convolution here, and then we have absolute values on y, then we have absolute value on this whole summation. Then next we just use triangle inequality. So we know this absolute value of summation is less than summation of absolute values, and also absolute value of multiplication is less than absolute value of all the terms. Okay. So this is less than the summation of this absolute value h and absolute value x over n minus k. And then finally, so first we use this this condition here. So we know our input is bounded. So this x over n minus k is bounded. So they are all less than b. And we are summing over positive terms. So yeah, so we can just replace this inequality with less than b. Okay. So this absolute value of x n minus k is less than b because this is true for every n or n minus k. And then we have the summation of k h of k absolute value here. Then finally we can use this assumption here. So this assumption says that the summation absolute value is finite. So here is some finite b times some finite value, and so total thing is finite. Okay. And yeah, so we prove that this is sufficient for your system to have BIBO, to be BIBO. Have a bounded input and we'll have bounded output. And for necessary, then we once again refer to another problem. You can look it up on the textbook. Okay. So any question? Absolutely summable and absolutely integrable, and how they are condition for stability for LTI system, and the proof. If not, then let's go to the example. Okay. Example, let's see some function we have seen. So first is the pure time shift. Okay, so we will say that pure time shift for discrete and continuous time, they correspond to the impulse response being just the unit impulse function shifted, and or the delta function. So for discrete time, the pure time shift will have impulse response delta of n minus n0, and for continuous time we'll have delta of I think it should be tau minus t0. It's a bit weird. Is delta of t minus t0, but we are integrating over tau, so delta of tau minus t0. Okay, so anyway, so those are time shift function, and we want to see whether they are stable. Okay, and well, then we do our check. So we check whether they're absolutely summable or absolutely integrable. So we take an absolute value, which does nothing because it's positive and positive definite. And so somewhere over them, then you see somewhere a whole bunch of 0 and 1, and the summation is 1. Okay, because it has a 1 spike somewhere, so the summation is just 1. And for the continuous time case, you have this integration. So once again, the absolute value do nothing because nothing is negative. And the integration is the integration of the delta function. And as we say, you're integrating over the spike of the delta function and get the area 1. Okay. And so both the systems are stable as said by as checked by our stability test on this impulse response function. Okay. And we can also think about this makes sense. And so what the system do is they are time shift. So you take some input and you just get a time shift output. So maybe let me draw a little bit. So the time shift right. So you have So they are time shift. So you have whatever input, then you just have a similar output time shift to somewhere. And so if the input is bounded, the output is also bounded. and so they should be stable, and that's good. Okay. And okay, so the next input is, I guess I should highlight this. The accumulator. Okay, so the accumulator we just seen today a bit is the accumulator with impulse response being U of n. Okay, and so it will keep accumulating, and we have seen on chapter 1 that the accumulator is unstable because you just put input with 1 1 1 1 then the output is going to accumulate to infinity. Okay, actually it's infinite everywhere, so it's a bit weird, but anyway, so with the constant input, the output will get accumulated to infinity, and the system is unstable. Okay, and we can also check the system is unstable from our impulse response. Okay, so we can also check the summation of impulse response. So summation of is u, and then summation u from minus infinity to infinity, then summation u from summation n from 0 to infinity. But u is just this function that keep having 1 1 1 1 spikes, and so the u look like this, right? Remember, u is this, so it's n, and it's 0 here. And when you try to sum over all those spikes, there are infinite number of them, so the summation is infinite. And so yeah, so the system is unstable as checked here. Okay, and similarly you can have the integrator, which is similar to the you can have an integrator that's very similar to accumulator for continuous time. So if your y of t is the integration of minus infinity to t x over t, then you find out that the integrator has an impulse response very similar to this u of n. It's actually u of t. So you can just check it by doing the definition of impulse response. That is, you put the impulse, you put delta function here, inside R0 x of t or x of tau here, and you check what's your y of t. And this is one of the relationship we have between delta of t and u of t. We find out that you integrate over delta of tau d tau from minus infinity to t. Then for t less than 0, you integrate to nothing, and t greater than 0, then you integrate through this delta of tau, and you got u of t. You got 1, so that's u of t. And yeah, so anyway, we find out that the impulse response is also u of t, and then check whether it's absolutely integrable. Then you see that, well, it's not, because just like this case, you have infinitely long u of tau that's just 1 between tau 0 to infinity, and that's infinite. And yeah, so the impulse response is not absolutely integrable, and the system is not stable as you probably imagine, because you put a constant function here, you also integrate to infinity. Yeah, everyone okay with the example here? We have our favorite time shift and integrator or accumulator here, and we see that they are unstable. So the time shift is stable, but the accumulators are not stable. Okay, and okay, but something interesting here. So hopefully this don't get you more confused, but it's very easy to confuse things here. So about stability. So you need to not confuse between absolutely integrable and bounded. Okay, so first thing is this absolutely integrable, absolutely summable. They are totally incomparable to whether a function is bounded or not. So first thing you need to remember is some property of functions. Okay, yeah, and so we have two counter example here. So delta function is infinity at t equals 0. So this is not a bounded function. It's a bounded function on diverge. But as we have argued, it's absolutely integrable. So there are functions that are absolutely integrable but not bounded. And on the other hand, this u of t we have seen is not absolutely integrable because the integration, so this integration will go to infinity. But it's totally bounded, it's less than 1 everywhere. Okay, so bounded and absolutely integrable or summable is incomparable. It's just two different concepts. And then when we think about system and stable, there are really three things here, and you need to not confuse what you are thinking about. Okay, and so our system kind of schematically look like this, or LTI system. So LTI system, you have some input x and some output y, and the system is described by h of t here. Okay, and so we have two definitions of stable. So first we say the system is stable if only if it's BIBO, means every bounded x gives you bounded y. So care where you are caring about whether your x and y are bounded or not. And then, so this is what we do in chapter 1. And what we just do is we say, well, the system is here, and this actually works for every system. Then on chapter 2, we say we can describe a TI system by this h of t. Okay. So we can also describe this BIBO stability by h of t. And what we are checking on h of t is whether it's absolutely integrable. We are not checking whether h of t is bounded or not. That doesn't mean anything. Okay, as we see in these two examples. Okay. Function, this h of t. H of t is a function that's describing your system, and it can be bounded but not absolutely integrable, and it can be not bounded and absolutely integrable. Okay, so when you check in, so when you check h of t, you should check the integration, not whether it's bounded or not. And but when you are checking x of t and y of t, you need to check whether bounded x give you bounded y. Okay, so hopefully this clear your confusion about stability, and so there are really two different ways to describe stability. Okay, and yeah. Let me write a little more. So this one is chapter 1 is works for every system, and this is chapter 2, and this only works for LTI system, because only for LTI system we can describe it by this impulse response h of t. Okay, and I think we have like 10 minutes, and it's actually enough to finish the rest of this section. The rest of the things are kind of not so important. I guess first, everyone understand here? Okay-ish? Okay, then let's finish with other property, other things here. So this 2.3.8, we won't use this too much, but it's nice to know the name. So we want to introduce the concept of unit state response. And unit state response is really similar to unit impulse response. So remember our H is a unit impulse response. That's when you put the delta function as the input to your system, your LTI system, then you get this H as your output. And the unit state response is very similar. You say your input is u of n or u of t, then the output is the unit state response, and it's usually written as s of n or s of t. Okay, so this s is our unit state response, and as we say, it's just whatever response you have with the unit state function as input, and you find out that you can write it, you can express it as h of n. And that's not surprising because everything about system can be described by h of n. So you do this calculation, s of n equal to, well, unit step as input, and the output will be convoluted with h. Then you say that's the same as h convoluted with u. And then you find out that convoluted with u, then it's a summation from minus infinity to n. Okay, so s is actually the accumulation of h. And they found out that we have zero that accumulation has inverse. So more interesting thing is this one. So h also can be written, can be expressed by s. So you can express h of n as s of n minus s of n minus 1. And similarly, so when you go to continuous time, the summation become integral. and the difference become differential. So h of t equal to ds dt. And so we found out that as unit state response, although we will not use it too much later in the chapter, but other places might use it, and they are very nice because they also totally characterize our system. Because you can calculate h from s, and really you can swap between h and s by those relationships, right? And yeah, so you can convert between h and s without losing information. And so your s also totally describe your system. So maybe sometimes you don't want to describe your system by h, then you can describe your system by s. Okay. So that's a unit stamp response. And I guess the most important part for us now is you need to remember the non-unit state response, and also the symbol s is usually reserved for unit state response. Okay. And the next one is variation of support and the length after convolution. It's actually quite an interesting concept, but mathematically it's really simple. So let's first talk about the support, or I guess the duration of the signal. We'll kind of talk about this. So first we want to talk about support of a signal. We think our signal usually is kind of physical. So the signal is a function, but we think it's physical, so it starts happening at some t1 and stop. So it starts at t1 and stop at t2. Okay, so signal like this, and then we just say the support is this interval from t1 to t2, and the length is just the length of the support, so it's t2 minus t1. And for discrete time is similar. I guess let's do continuous time first. Okay, so support is this, and then we can show. So our signal has a support, and our impulse response also has support. So our h of t maybe also has a support t3 to t4. Okay, so support of x is t1 to t2, and the support of h is t3 to t4. And we now think about the output. So what's the support of output? Then you can easily check that the support is kind of the summation of the two support. So the support of the output will be t1 plus t3 and t2 plus t4. And the length will be just, so length is just the length of h plus the length of x, okay, adding together. So yeah, so mathematically is really simple, but it's an interesting concept. So you see that your system got convoluted with something to output, then the duration you're adding together. And it's really similar for discrete time. So discrete time you also have some support, so you also think you start at some finite some n1 and stop at some n2. And you only have finite value between n1 and n2. Excuse me, n1 and n2. And so the support will be this interval of n1 to n2. And the length of this interval, you do some elementary school counting, and you find out it's actually n2 minus n1 plus 1. It's just, this plus 1 is, you can just check it by some example. There should be a plus 1, because you are counting both the head and the tail of this interval. And so really similar thing. So you also have support for your impulse response h. That's from some n3 and n4, and you find out the support will be just support of the output. When you do the convolution, it should be just between n1 plus n3 and n2 plus n4. And the length, when you do the counting carefully, then the length is plus 1, is 1 plus 1 here will become, because you want the 2 plus 1 to on this length of x and length of h, then in the end you get a minus 1. That's elementary school math. I guess I could go a bit too fast, but that's all for today, and we have 5 more minutes, but next time we'll start talking about LTI system, and I guess LTI system related to differential and difference equation. So we'll go to some differential and difference equation that can be described by causal LTI system, and we'll kind of solve them. Will I solve them? But anyway, we'll describe our system by LTI system, and we'll describe those equations by LTI system, and we'll learn about them. Okay, so that's all for today. Any question? Otherwise, I think we can stop 5 minutes early today. Oh, actually, yeah, 5 minutes right. Yeah. Okay. So see. Oh, yeah, question. 减一吗？蓝色，为什么是 N 加3吗？就算了，就会知道。我想想看有没有什么 intuitive 想法，我没有太想，但是就看起来还蛮合理的。然后我想想看，对啊，是交集的时间。我想想看，我能不能？好，我们还有时间，所以我可以试着画画看。我想想看，所以如果 x 是在这里的话，对啊，是交集的时间没有错啊。所以 x 有个 n1 到 n2嘛，然后 h 是我想想看 n3 到 n4的话，x h，然后我们要很辛苦的画出所以 h over n 减 k。h of， 然后这是 h over n 减 k， 要在例如说 n 在这里好了 ，n 在这里，然后我们会有这里是负 n3。OK， 我是用 continuous time 来写的感觉，但是应该差不多吧。负 n3 到负 n4， 负 n4 对吧？然后所以什么都会交集，我们要到然后所以这两个要交集的话，那就是 n 要大概是 n3， 然后这两个会相加嘛，就是这两个要开始重叠的时候是这个东西在这里对吧？然后这里是 n 等于 n3， 然后这个就是在0上，对吧？然后所以是从 n 等于 n3 开始交集的，然后一路拉过来，它们两个会重叠，然后到最后，然后到不交集的时候是这里是 n2， 然后 n2 要等于，然后 OK， 所以这是 n 减 n3， 这是 n 减 n4， 然后最后交集的是 n2 等于 n 减 n4 的时候，对吧？那就是 n 等于 n2 加 n4。Okay. yeah. So that's okay. So sorry. That's what we're trying to. So, but in English, so we were trying to derive why is this. Suppose n1 plus n3 and n2 plus n4. So we think with some function support n1 to n2, and another function that has support n3 to n4, and we try to show how the convolution overlap. And also we draw this h of n minus k, and h of n minus k we know n at some point here, and it's like so 0 will go to n, and we have the time reversal. So n3 will become n minus n3, and this n4 point become n minus n4. And we see how where n must be when this thing has overlap. So it has starting overlap when n equal to n3, and this n minus n3 becomes 0. And it stop overlapping when this n minus n4 becomes this n2. And so n minus n4 equal to n2, then n equal to n2 minus n4, n2 plus n4. And here we have, sorry, this is not 0. So here we have, and so, anyway, and here, so the starting point is, so this is n1, right? So this is n1, and where n equal to n3 plus n1, then this point will be n1, and when n equal to n2 plus n4, then this endpoint, this n minus n4 will equal to n2. Okay, so I guess we are exiting on time, and so see you on next Tuesday.